Это мое. У тебя свобода. Вот. So I think the second stage this morning, Avraham Aizenbud, the wife of these, and the type of the talk might be right. What happens when you push measures using polynomial maps? A dictionary between algebraic geometry and analysis. Take me there.
So, thank you very much. Thank all of you very much, and especially thank you very much, Boris. I'm very happy to see you after all these years, and I was very happy to study under you for many years before that. We'll try to say something more informative in the evening, but now I would stop first, wait for your time, and try to talk about the topic. So this talk is based on several works, joined with Nir Avni and Shachar Carmeli, several with Nir Avni and one with Shachar Carmeli, but in fact, will be kind of overview of, and of course will be many works of other people which I have nothing to do with. So let's start with some general setting, or maybe not start with a general setting. We have a local field. So what does local field means? So there is a formal definition: a locally compact, non-discrete topological field. Okay, maybe it sounds a bit too abstract, but in fact, there's very limited. Okay, I will try to speak out. This one is the problem.
It's a globe filled outdoor.
Yes, so there's very limited bank of examples. No, it doesn't work. Yeah. So first example is R. Next example is QP, the field of periodic numbers. Next example is this fine field of Laurent power series, formal Laurent power series, with coefficients in a finite field, say FP. So what does it mean, formal power series? So I mean that there are finites from the left, so finitely many negative powers and infinitely many positive. And then you can take finite extensions of all of these examples, and this is basically all what you get. Yeah, so finite extension of R, I guess you all know, only two of them. And finite extension of QP is kind of complicated story, but anyhow, they're all finite extensions of QP. And finite extensions of this field, so it depends how you think about it. The extensions themselves can be again complicated story, but if you just care about what is the extending field and you don't care about the extension, then in fact they're all basically the same. With instead of FP, you have FQ.
The most important field, so the field of complex numbers appears as a finite extension of R.
Yes. Yeah, it's probably not the most important local. Or maybe it is one.
Finite extensions of R.
Yeah. Yeah. So he is not here. But...
So algebraic numbers are
not local field at all. Yeah, so the idea is that this is a nice framework for doing analysis. So this talk and in general, what I like to do is take algebraic geometry, something that's defined by algebraic equations, but then you try to do analysis on these objects, which are algebra geometry. And at least for general field, I don't know how to do analysis, and probably for really general, it's not possible. Of course, this is not the end of analysis, but this is like the basic framework where you can do analysis almost in the same flavor you do it in R, but a bit different. For one hand, and for the other hand, if you want to understand some global fields like Q, for example, which is in a sense much harder to understand than all these examples, because okay, it's maybe simpler as a field, but if you try to solve equations over Q, it's become a really hard question. And so one way to approach it is to understand the local fields, and in a sense, when you understand all local fields good enough, then you at least can start to ask global questions. So I didn't get to that level of starting asking global questions, so I'm start asking local questions, and this is a list of fields. Okay, and I will not use this. Sorry. So now we have x and y, which will be two affine spaces over f. So basically f to the power n and f to the power k. And in fact, more generally, it's better to think on smooth algebraic varieties. But if you don't want to know what are algebraic varieties, so you can understand most of the talk just by limiting to affine spaces. The most interesting phenomena already happens there. And certainly you can talk about affine algebraic varieties, and everything is local, so you don't do it. And now we have morphism from x to y. So what does it mean, morphism from x to y? It just means a tuple of multivariable polynomials in case of x and y are just the affine variety. So if you have x is f to the n and y is f to the k, so you have k polynomials of n variables. So this is your algebraic data. Now, when you think about x as some abstract algebraic thing, we call it affine space, an, or affine variety, or just a variety. And when we want to think about it as something topological, and then we talk about the f points of x, and then we will call it f to the n. So we denote it by x of f. And if it is actual algebraic varieties, then there are some equations, and this is a set of solution. And these, of course, have topology that comes from the topology of f. And now we can consider on x notion of smooth compactly supported measures. So measures, you all know what measures means, but we will restrict ourselves to Adon measures, which just mean, we can think about it just functionals on continuous functions, compactly supported continuous functions. So, like nice measures, yes. But what does it mean for a measure to be smooth? So for this, we need to kind of choose some standard measure that we will consider as like the basic thing. So if we're working with Fn, this is just a Haar measure. And then we multiply it by a smooth compactly supported function. And then we, of course, obtain compactly supported measure. And by definition, smooth measures are measures that obtain in this way. And this is not so sensitive to the choice of this standard measure. So, of course, Haar measure is defined only up to a constant, but this space will not be affected by it. But even if you say, okay, let's talk about something global, some variety, you don't have, if it's not a affine space, you don't have Haar measure, but it doesn't really matter because the notion of smoothness is a local notion. So you can work locally, and locally, in a sense, you can replace your variety with a affine space. Now you can say, no, it doesn't work like this in the algebraic world. You can locally choose polynomials that will map it isomorphically to a affine space. But the notion of measure also exists in the analytic world. So if you're okay with working with analytic geometry over the field F, then you can define the notion of smooth measures over X of F. And if not, then we'll discuss it further how you can do it in a sense without going to the analytic geometry world and stay algebraic geometry. Okay, so the good thing that we can do with measures, we can push it forward. It's an easy procedure once you have a measure. So a measure of of the push forward measure, so of a set in the target, is a measure of its pre-image in your original variety. And since your measure was finite, was compactly supported, then the push forward is also finite, so it's also compactly supported. What is not true, the push forward of a smooth measure is of course not necessarily smooth. The simplest example, you have embedding of a point to a line. You can take, there's only one measure on a point and it's smooth. You push it to a line and then it's not smooth at all, it's atomic measure, nothing smooth about it. And this is the main framework for the talk. We want to study this space of measures that obtained as push forward of smooth measure under a given map phi. So basically the main question is how to relate the algebraic geometry of phi to the analytic properties of this space. So what do I mean by algebraic geometry of phi? So the two affine space doesn't really have interesting algebraic geometry because they are affine. And since we're doing everything local, so smooth variety also doesn't have interesting algebraic geometry. But the map phi itself does have interesting algebraic geometry. For example, its fibers might be very singular, complicated, and whatever. So this is what we want to understand, the relation between P and this space. And there are two aspects of this question. One is on the level of the individual measure. So we take smooth measure, we push it and ask how bad can it be. It's not smooth, but maybe it's not so much worse. And another, you want to take the collection of all smooth measures together, send them, push them down, and then ask questions that are not relevant to individual measures, but for all together. For example, how much of them, how much they differ one from the other. So we will try to talk about both of these aspects. And so both these questions related to number theory and representation theory. I will not go into these topics, but I just will say very shortly why they're related. So in representation theory, when you do compact groups, then there are many interesting functions that you study on the group, say character of a representation, matrix coefficients, etc. Once you go to non-compact groups, often these functions stop to being functions anymore. If you try to define analog of these functions, the non-compact groups are not functions, but they are generalized functions or distributions, which are not necessarily measured, but often they are measures. And in any case, you can relate them to measures. And so this is one way this question pops out in representation theory. And what happened in number theory? So maybe the most basic question of algebraic number theory is how to count number of solutions of, or how to even say whether the differential equation has a solution. Maybe it's too hard question, but it's kind of fundamental question. Or instead of saying how much, whether it has solution, you can try to ask how many of them, and then you can study your differential equation modulo powers of P. Of course, it's much easier question. Solve equation in integers is very hard. Modulo powers of P, you have kind of a chance. And it turns out that okay, you can take modulo any integer but then you have J reminder theorem, so you can replace it with power of P. And then it turns out that studying this question is essentially study volumes of the push forward measure. So we start with some simple-minded smooth measure, say characteristic measure of a ball, and then you push it forward, and then you ask what are volumes of some smaller balls. One thing that I forgot to say, I'm sorry, what is smooth? I say smooth measure is defined using smooth functions, but what is a smooth function? So in the real case, you all know what are smooth functions. In the PRD case, and PRD here also mean non-Archimedean in general, so also positive characteristic non-Archimedean is FP of T, and smooth just mean locally constant. It makes life much easier in the PRD case. Okay, so let's continue.
For C smooth functions are just
smooth. Okay, so now we started with measures, but we asked how much they're not smooth, and it's easier to define this property for functions. So how we go back from measures to functions. We want to work with measures because it's easy to push measures, but when we ask whether something is smooth or not smooth, we prefer to, or something else, we prefer to work on functions. So for this, we need to choose not only standard measure on x, but also standard measure on y. Again, if it's a fine space, it's not a problem. And then you can consider kind of a ratio. Each time you have a measure, like this is a space of measures, so this division, I mean, element-wise division. So you take one measure here, and then you can try to divide it by mu zero. So what does it mean to divide the measure by a measure? So in general, it doesn't really mean too much. So there is the Radon-Nikodym theorem that says that in some cases you have the Radon-Nikodym derivative, and then you can divide measure by measure and get a function. But even if you can't, if you're working in like two-reasonable settings.
Sorry, when you choose a standard measure mu zero, aren't you assuming that it is in a sense non-vanishing? So
The mu zero, I want for now just the Haar measure. If it's a vector space, I just want Haar measure. Otherwise, yes, I need to assume that it is smooth and non-vanishing and very nice. So locally looks like the Haar measure.
So then the problem comes not because of the denominator,
because the numerator, yes. Yeah, so if I don't know anything about the numerator, so I don't know what they mean. But in general, there is this notion of Radon-Nikodym derivative. And even if it's not really defined as a function, for any reasonable, for any measure that we discuss here, it will be defined as a generalized function, which is more or less a definition of generalized function. It's a distribution divided by some standard nice measure. And so, in general, I can say generalized function, but it doesn't give you too much information. But yeah, maybe the first question that we can ask when it is an actual function, and once it will be an actual function, we can ask whether it's a good function or bad function. Okay, it's not smooth, but how bad it is. And okay, so now I would try to explain the answer to this question when it is an actual function. And for this, I need to to say things a bit more abstractly. So if X is an arbitrary algebraic variety, smooth algebraic variety, we have the notion of polylinear top differential form or multilinear top differential form. So it means that in each point we take the tangent space and choose a top differential, top multilinear form or polylinear, how I should say, on this space. So you all know you have n-dimensional space. There is one-dimensional space of multilinear forms on this space.
So you allow for the degeneracies, but the on algebraic sense.
No, so degeneracy means that it might vanish. Yes, it might vanish, but it's given by a polynomial. So it's a very, very smooth and nice function. So how to define whether it means that it's given by a polynomial? So for a fine space, it's very easy to define it because in this case, the tangent space is all the same. So we just have this standard form, and then we can multiply it by any polynomial. But in fact, in algebraic geometry, there is a way to do it for any algebraic variety. And now each time we have such a form, which is completely algebraic gadget, we can define a measure. And how do we define a measure? It's called the absolute value of the form. And the formal way, I would say only formally what does it mean for a fine space, but in fact, you can do it for any smooth algebraic variety, and in fact, even for any analytic variety. So for a fine space, it's very easy. You take the absolute value of the polynomial and multiply it by the fixed Haar measure with respect to like this coordinates. Yeah, so it seems that I didn't say anything because I just say on a fine space we have the standard Haar measure, so each polynomial gives us a new measure. But in fact, it is better than just saying that polynomials gives measures, because you know that when you take change of coordinates, you need to pay some prices. So your measures change, and it's not given by the same formula. You have to multiply by the absolute value of Jacobi.
So you have some absolute value on your fields?
Yes, yes. So the all local fields all have absolute value. So R and C is an absolute value that we all love. In fact, for everything to work properly on C, it's sometimes better to choose the square of the absolute value. But okay, it doesn't really. It's not satisfies the triangle inequality, but it's okay. And for all QPs, you have
FP of T, you use some relations.
yeah, it's very similar to QP. Yes, so you take P to the power of the negative valuations. So you just postulate that T will be of absolute value 1 over P, and then everything else has defined basis. And so once you have this absolute value, you can take a form and convert it into a measure. And so unlike polynomial or function that you can convert into a measure, but it's really sensitive to your standard measure that you choose, this thing is more or less completely canonical, except of one thing that you once and for all have to decide what is a standard measure of on f to the n, which, yeah, maybe there is more than one good answer to this question. So on r to the n, or on R, we kind of love the Lebesgue measure, but on a general local field, we usually will prefer a measure that will be normalized on the unit ball to be 1, and so it will not be the Lebesgue measure, it will be half of the Lebesgue measure. But okay, it's not really important. So you have this completely canonical procedure starting with volume form and getting top differential form and getting actual measure. So over R, it's very standard procedure, but basically the same thing works over all the local fields. Just the notion of absolute value is much more aggressive over local fields. So over R, we take absolute value, what real stays real. Here we start with something which is the adic value, the Omen is algebraic gadget, it's a value, it's a defining field. But after the absolute value, everything becomes real. Okay. So now we can try to compute the density function. So we will not do it as the first step. We will not do it. So density function is this ratio between the push forward of a measure and the standard measure downstairs. So in the first step, we will not do it for general morphism, but only for smooth morphism. So in algebraic geometry, when people say smooth, they don't mean that the map is given by the coordinates of smooth functions, because this is always true, and because everything is polynomial in algebraic geometry. But they mean what in differential topology called submersive. So that the differential is an onto map. It kind of makes sense from point of view of algebraic geometry, because if you consider your map as a family of varieties, each variety is a fiber of a point, then to say that the map is smooth is in a sense equivalent to say that the fiber, not really equivalent. Relate a stronger version of saying that the fibers are smooth.
When right differential, so it is a pointwise differential. So it's
For each point, the differential should be onto map from the tangent space to the tangent space downstairs. Very simple.
so if you recall the Sartre theorem in this context, it means that the exceptional variety, the exceptional set, is not just negligible but absent.
Yes.
So your Jacobian has maximal rate here.
Yes. So start with this case. This is called smooth. And now, general lemma in linear algebra, each time you have a vector space which is extension of two other vector spaces, then the one-dimensional space of top form of the middle guy is a product of these two one-dimensional spaces. Okay, so this is just equality of one-dimensional spaces, so they're all isomorphic, but here, of course, it means that they're canonically isomorphic, and it means isomorphic in a way that preserves all the symmetries. And the reason why it works is that each time you have block upper triangular matrix, and you want to compute its determinant, then you don't care about what's written here. You only care about the product of these two determinants. So it means that when you have symmetry of such situation, and the effect on form W is controlled by these two effects, and it's a product of these two effects. And this translates into this isomorphism. And this allows you to define the Gelfandler form. So you start with a map for x to y. Now I want to pick some standard form on x and on y. So if x and y are affine spaces, then I just pick the actual standard form. If not, yeah, maybe I should have told it before, sorry. So on any, okay, not on any variety, one have a global invertible top differential form. In fact, even one might not have global top differential forms at all. But locally, and this time locally in Zariski topology, so any algebraic variety, you can cover it by smaller algebraic varieties, open sets which are algebraic varieties, on each of which you do have invertible top differential form. And so once you pick this invertible top differential form, you can define its absolute value and think about it as your standard measure. And the density function of this standard measure will be invertible with respect to any other choice of standard measure. So because you remember you have this absolute value of the polynomial, so I say invertible, I mean smooth. So absolute value of a polynomial is not necessarily a smooth function, but if the polynomial does not vanish, then it's actually very smooth. So you pick a standard measure, standard form on x and then y. So maybe you have to make them a bit smaller for that. You don't care. Everything is local. And you consider the fibers of the map. And the idea is that you can construct now a form on the fibers. How you construct this form? But first of all, what do you want from this form? So you want that each time that you take a smooth measure on x, so smooth measure on x is given by definition as a smooth function f times absolute value of omega x. You push it down, you take density function with respect to y, you ask what is the value in the point y, and then you get the integral of your function f over the fiber with respect to this special measure, which is obtained by this special form. So this form will be called the Gelfandler form. And how do you construct it? You can do it in each point separately. So we take a point in x in the fiber, maybe a point. You have a point in the fiber. This is say x is a plane and y is the x-axis, sorry. And this is the fiber. So you have the differential, which is a map between the tangent space here and the tangent space here. So the kernel of this map is exactly the tangent space to the fiber. So we have a short exact sequence like this. When in the middle you have the tangent space to x, and in the right hand side you have the tangent space to y, and the kernel on the left hand side you have the tangent space to the fiber. So you're given a form on x, which is form w, and form on L, but form on y. So you use this formula to divide the one by the other to get a form on v. And v is the tangent space to the fiber. So you can construct the Gelfandler form, and it's rather easy to check that this equality holds. And in particular, we see that if the map is smooth, then the push forward of smooth measures are smooth functions. And so basically this is the most boring case, no new information, but you get just as simple as possible object that possible to get the smooth functions.
But this form on the fiber is not polynomial.
And it is algebraic.
It is polynomial.
Yeah, all this procedure was. But I have to be a bit careful because the fiber itself is algebraic variety, but it's not a fine variety, so it not really means that you can you cannot choose some algebraic coordinates on the fiber and write it as a polynomial in these coordinates. But if you consider it as an algebraic variety, so locally you can it's a fine, you can embed it into a fine space, and then everything is obtained by restriction of polynomials from the fine space in this form. So like polynomial on algebraic variety.
So it's a polynomial and metaphoric sense, like algebraic function.
Okay. So one corollary that we get here, that what I said, that in the smooth case, everything is boring. Or in fact, in a sense, the following are equivalent. The morphism is smooth, and the push of smooth compactly supported measures are smooth measures, so the density functions are smooth. Yeah, so as it's written here, it is a lie. So what is correct?
You mean the second condition also implies the first?
So this is a part that is a lie. So the truth is the first implies the second, and now it's not a lie anymore. And now the second implies first. So there is a general problem in all these themes. So if you want to do such a dictionary, say algebraic geometric condition equivalent to some analytic condition. So one direction is perfectly good. Yes, you have some algebraic geometric condition. It's imply you can prove that it implies some nice analytic conditions. But the other way around basically never works because if you do it naively, because you can take the most horrible variety that you can think of, and then to multiply it by the variety of solutions of this equation over R. And you know that the set of solutions of this equation is an empty set, but the algebraic variety of solution of this equation is not an empty variety. It just have no real points. It has two complex points instead. And then you just killed your variety on the level of points. So now it's the best variety in the world on the level of points. So any analytic requirement will be satisfied for it because empty set satisfies more or less everything. And it will not imply anything about your algebraic geometry of your original variety. And so in order to correct it, if you want implication to the other direction, you always add here that some analytic property that you come up with have to be satisfied for any field extension of your finite field extension, finite field extension of your original field. So if you work in the real case, it just means that work with C and forget about R. But in the case, you cannot work with QP bar because QP bar is not a local field. But if you work with all the extensions of QP, then you have. Okay, so
I'm explaining him that morphism P may be smooth at all f rational points, but is not smooth
as a
as a morphism.
Of course, yeah, one can in most cases one can formulate everything more carefully, like with this delicate conditions that not really smooth, but smooth somewhere or not. But then it become in other things it become more complicated. So I want to make my life simple. Okay, so if we're imagining that we're building a dictionary between analytic properties of these push forward of measures and algebraic properties of the morphism, so here we already got our first lines dictionary. Okay, so now let's go to maybe the last line in the dictionary. Let's talk about generically smooth. Okay, so what does it mean generically smooth? It means that there is an open dense set in the source where the map is smooth. And this is almost always the case. I will comment about it. It's not really always the case, but it's really very large generality for maps. And then the statement is that the density function is an L1 function. So L1 function are not the worst case scenario of functions in the world, but if you want your function to define a measure, then it's better to be L1. So of course there are worse measures than L1. And indeed, if your map is just embedding of a point to a line, then it will not be L1.
We don't distinguish between L1 and L1 local.
In this case, it doesn't really matter because they push completely supported functions. But you're right, it's better to write here L1 local. Formally it's equivalent, but we want to understand local property of the function. But all of our functions will be completely supported, so local properties are also global. Okay, so what is this condition of generically smooth? Of course, here you have to add for field extensions. What is the condition of generically smooth? So in characteristic 0, you have much simpler way to say this condition. It just means that the map is dominant. Dominant means that the image is dense or of full dimension. It's more or less the same if everything is irreducible. For map from A to N, you want the image to be a full dimension. And in a sense, you can say that if the image is not a full dimension, then you replace a target. You can replace a target by the closure of the image, and then everything will work as well. So why to bother with non-dominant maps? It's not completely true because the image might be singular, and then we don't really know what are densities of measures on the on the image. So it's not the dominant case, it's enough for everything, but it's really very large generality. And also this equivalence also only work for characteristic 0. So in characteristic 2, you have the map x maps to x squared, and it is dominant, it kind of onto over the algebraic closure. Its image is Zarinsky dense, but on the level of the local field, if you can figure E of t, so the image becomes a very small portion of this field. It's kind of a subfield of this field. And of course, the push will not be smooth, so it will be supported on this small portion. It will not have a codimension from point of view of algebraic geometry. It will be Zarinsky dense, but somehow analytically and geometrically, it will be of the dimension half of. If this is one-dimensional object, this is going to be a half-dimensional object. Not half-dimensional in the sense of fractals. It will just look like the same field. So this field is extension over itself, and it just will be a subfield of this field, and the degree of the extension will be 2. Okay, so how do you prove this lemma? It's rather easy. You use the previous lemma, the previous corollary that you know have everything for smooth measures, and you use our Zonic theorem. Then it's rather easy. Yeah, and of course, the most interesting direction is while 1 implies 2, and the other direction is usually less interesting, but it's also almost as easy. Okay, so now we can start to build our dictionary. We have the first and the last line, but I write it as the first and the second line. C infinity functions corresponds to. Maybe for the dictionary. In this setting of dominant maps or generative smooth maps, we can talk about density functions, and they will be L1 functions. This is what we got before. So all the properties of measures, instead of formulating them in the language of measures, we can ask properties of functions, how properties of functions correspond to properties of algebraic maps. So smoothness of a function corresponds to smoothness of the map, and just L1ness of the function, which means nothing for in our setting, corresponds to the fact that the map should be generically smooth. And you have lots of things here in between. Yeah, so C infinity is more or less the best thing you can think of. L1 is not the worst thing you can think of, but 1 is the worst. So notice that all of the LPs are better than L1 because we're working locally. And L infinity is better than all of the LPs, but still L infinity is worse, L infinity log, yeah, is worse than C0, which is much worse than C infinity. So in the middle between these two lines, we have this middle line, which a priori can be two middle lines, C0 and L infinity, continuous functions and locally bounded functions, and we can ask what they correspond to in algebraic geometry. And here we have an answer. But before getting the answer, how we can approach such an answer? So we still have the Gelfand-Leray measure. So it will not be defined.
Functions are still polynomial, right?
The function, the maps are polynomial, but the measure is.
Yeah. But when functions come from ratio, right?
Yes, this column is analytic column, this is geometric. Yeah, so here the word smooth means submersive. Yes, it's not, and generically smooth means generically submersive, which almost always satisfying the Sar's lemma more or less. And here we need some algebraic gadget. So on each fiber we have the Gelfand-Leray form, just unlike before.
Convergence means a convergence of integrals over the pre-images over fibers.
But did I say something? Yeah, you're right. But yeah. So this is what I want to say. So over each fiber, we have the Gelfand-Leray form. So in principle, we have a formula for, but this form does not define everywhere. It's defined only in the smooth points, which usually can be an open set inside the fiber, and maybe in some fiber it doesn't define at all. But even when it does define, it's defined in an open set, and so you can try to compute its integral. But then, even if your function is completely supported, the integral might not converge. Because when you go to the singularity of the fiber, things might happen. And at least on the intuitive level, it seems very related to the question whether you are given by a continuous function or a bounded function. Because L1 function is not, so L1 function also given by this integral, but L1 function allow not to be defined, it allow to be infinity somewhere. So maybe generically, as you have the third lemma, so generically the integral converge because it's smooth, because everything is smooth. But once you go to some bad points, the integral will not converge, and it's allowed for L1 function. But it's not allowed for an infinity function or for C0 function. So you want the integral to converge everywhere, at least it seems to be relevant to the question when you get something continuous. Okay, so here we want to formulate this idea of integral of a form converging. So now we start with algebraic variety Z, and now it's important that it's not a fine space because it's not going to be smooth, it's going to be one of the fibers. And suppose that, so we will call this variety integrable if for any top differential form on its smooth locus, the absolute value of omega, this measure, which is now only a measure on the smooth locus. So we want this measure to define a locally finite measure on the entire set. So it's a compact set in Z, which is not compact when you intersect it with a smooth locus, still will have finite measure. And of course, we want the same for field extensions. And what I didn't write, but I should have written, we want it locally on Z. So if Z is have some non-trivial global structure, it might be that there are no top differential forms. So it doesn't mean that I want no condition. So I want locally on Z, and then you, I like that then you always have a top differential form, I think so. It might be non-invertible, but you always have top differential form on the smooth locus. So in this case, we will call our variety integrable.
What is locally finite?
For a measure to be locally finite, that if you take a, say, compact set, I want it to have finite measure. Or in any point, there is a neighborhood that has finite measure. This is equivalent because that is locally. Of course, I don't expect that the integral will converge over all Z, but we start with a compactly supported function on Z. But it's not compactly supported on the smooth locus of Z. Okay, so here is a statement. And so I write here assumption of existence of resolution of singularity. So you all know that existence of resolution of singularity is a theorem, Hironaka's theorem, but it is theorem only characteristic 0. And what I'm saying now, 2 even in positive characteristic.
Was he? Under assumption for
No, for all the, okay, for several varieties over the field, I don't. Maybe in this case it's enough to. No, you need more. You need some uniqueness also. How you usually, when you do usually resolution singularity, you have Z and Z prime and Z double prime. You have 2 different resolutions. One is strict, so it takes a fiber product and then resolves fiber product, and then you get one resolution to the model. So you need more resolutions. And then we have 2 equivalent conditions. One, which is this analytic condition of being integrable, and the other, which is pure algebraic, although it depends on the existence of resolution, that there exists a resolution such that if you start with a form like in the definition and you pull it back to Z tilde, oops, it's not written well here, so I should explain better. So you start with a form Z. Yeah, so you start with a regular form omega on Z smooth, and then this thing, which is, you pull it back to Z tilde, so it's not really a form on Z tilde, it's still form on the smooth locus, but you can think about it as a rational form on Z tilde, it just might explode there. And now I want it's not is regular, but can be extended to a regular form on Z tilde. So any smooth form on Z, once you pull it back to Z tilde, a smooth form on the smooth locus of Z, once you pull it back to Z tilde, can be extended to a regular form. Yeah, so it's pretty easy to see that once you have this, you can integrate omega, because instead of integrating downstairs, you integrating upstairs, and upstairs everything is smooth and nice.
But can you the second condition express in terms of the singularities?
Okay, so it depends how you ask the question. So in a sense, this is expression in algebraic terms. You just need to find a resolution of singularities, and in the characteristic zero at least, there are procedures of doing it. So this is kind of you can have a computer program that will check it.
Really, so for any range, so my computer form as input will get all regular forms.
Yeah, this is not a problem. Yes, you can have a basis for regular
So
forms.
basis is an
Yes, basis of the ring of polynomials.
Can you see this more generally, please?
Okay, this is a problem. So I would say it in a moment. In characteristic zero is another statement is that if you in addition assume that Z is Cohen-Macaulay, which is some properties, algebra geometric property, but in our cases, all the varieties that we'll discuss will be Cohen-Macaulay, and the characteristic is zero, then any of these two things is equivalent to the fact that Z have rational singularities. But rational singularity is some notion from singularity theory, but it's not really good news because the definition of rational singularities, the original definition, also looks like something like this. And so you can just use this as a definition if you. But there are some theorems that express the rational singularities, at least in some cases, in like more algebraic language, but more algebraic language sometimes, in a sense, it's worse because it looks very nice and Cohen-Macaulay. No, not smooth.
It's less than that.
Cohen-Macaulay, which is a rather weak condition, which all our sometimes it's strong, but in our discussion, all the varieties will be Cohen-Macaulay. We will apply it to the fiber of this map and fiber of a map between smooth varieties. Okay, not exactly correct. So I would say in a moment. I will say in a moment what why we think is important. Yeah, but in a sense, this the other condition for equivalent condition for rational singularity is sometimes worse because they look very algebraic, but you have to check something for any integer n, and so it means that you can't do it by a computer. So this condition and the usual definition of rational singularity is checkable by a computer.
In the definition is for any unitary form of this spectrum.
Any top form of the smooth locus, but
Takes the form of arbitrary high order the single.
you cannot really. So if the singular is of codimension 1, then you're right. But then it means that it will never be integrable. But if the singular locus is of codimension 2, then algebraic geometry doesn't work this way. Yeah, you cannot.
Right, it's not necessarily normal.
Okay, so rational singularity is always normal. So a statement is that if you know it for any form, then if it's Cohen-Macaulay, then it's normal. So without the Cohen-Macaulay assumption, then formally it's not. So. But it's of course you're right that this condition already implies that the singularity have to be of codimension 2, which is not exactly normality, but it's not that far from. Okay. So this proposition is rather easy, as you usually say. One direction you see easily that if you have the form that the integral converge, and the other direction, if the integral converge, then the form cannot have a real pole. If it's have a integral of 1 over x does not converge. And in algebraic geometry, you don't have 1 over square root of x, at least not now. So if it's regular, then it's converged, and if it's converged, then it's regular. So it's not. Okay, but now we want to kind of put it in a family and see whether we have whether we can get a condition for the density function to be continuous or bounded. And for this, I need the notion of of flat map. So if you don't know what is flat map, it doesn't really important. And because here is a theorem that give you equivalent condition for flatness in case that both varieties are smooth, and this is our case. A map is flat if and only if its fibers have constant dimension. And what this theorem gives us is that following our equivalent, the map is flat and have reduced fiber. So what does it mean have reduced fiber? So the fiber is kind of solution of equations, and we don't want to have double root. So x squared equal to 0 is the fiber maybe looks smooth. Yes, at each point the fiber is 1 point or 2 points, but it's cheating because it's have a double root. So reduced fiber, and the map. So this is one condition, and the second condition is that the map is not only generically smooth, it's generically smooth on each fiber separately. So on each fiber there is open set of smooth points, smooth meaning similar things. And yeah, okay, it follows rather easily from this miracle flatness. Or maybe I should give one example of non-flat map. And the blow up from a plane to a plane. It's not flat. And you see all its fibers are smooth, but the map itself is not smooth. It's a fiber over 0. The fiber is smooth, it's reduced, it's very nice, but the map of the fiber over 0, it's not a smooth map, it's not a submersive map. The differential cannot be onto because it's a one-dimensional kernel. So if it's a one-dimensional kernel, then its image cannot be two-dimensional. Yes, so the fiber is 0 and kind of look like a projective line, like a circle, and in all of these points, you have at least one-dimensional kernel, which is just a tangent space to the fiber. Yeah. It's okay.
What do this mean? It is really don't write it to tilde. You said blow up.
Oh, so
Okay.
so
What is to E is generically smooth in each
in each fiber there is an open dense set of smooth points of the map, not of the fiber.
But if you have a fiber and the web is just 1 point.
Yeah, but I want the points with smooth map of phi, not of the restriction. They should be smooth points of phi. So the differential of phi should be onto the target and time and space to y.
I do not find this thing.
So this is slightly stronger than ask flatness. So flat means it's a dimensional constant, but still you can have x squared, which is flat, but not generically smooth in each one. Yeah, so we see that flatness is kind of basic things that we need in order to make sense out of the Gelfandler reform. Otherwise, there will be some bad points where the Gelfandler reform will make no sense. But also we want it to be reduced, so then we actually can make sense of Gelfandler reform, and then we can even try to ask whether the integral converges. And I will call them FRS, so flat with fibers of rational singularities, if it's flat, and its fibers have rational singularities. So here I add and reduced. Formally speaking, reduced mean rational singularities implies reducedness, but it depends how you define the fiber. So if you work in the language of algebraic varieties and the fiber is kind of by definition reduced, and then it's not doesn't give you new information. But if you work in the language of schemes, and rational singularities implies. And rational singularity, so now we're working with characteristic 0 is equivalent to this integrability condition. Okay, and here is those results that I want to talk about. So it works only in characteristic 0. So the following are equivalent, P is FRS. The density is continuous function for P extensions also. And it bounded function. Okay, I forgot here one name now, sorry. So this is our theorem for the PIAD case, but in the Archimedean case, there was new students that proved it, and I forgot to put its name. I'm really sorry, now I don't remember his name. And so I will send the updated version of the slides.
Sorry, so you're saying that if it's bounded, then it automatically continues.
Yes.
It's automatic continuity.
Yes, yes. So if it's bounded, then it continues. But what is kind of more surprising, I think, is that if at each point separately the integral of Kliefeld form converging, then also it is locally bounded. And this is not obvious
The
at all.
trivial direction is from the third line to the second.
Oh, no. From the first line to both of the lines.
Or
it
the
is-
third line.
No, the main non-trivial direction is from the first line to the other two. Okay, from the third line to the second, maybe to do it directly it's also hard, but it's probably hard to do it directly. But what is relatively easy is from the third line to the first line, and from the first line to the second, it is hard. So for the harder thing is from first to the second. And this is hard, and I don't know how to prove it in positive characteristic case. So formally speaking, it doesn't make sense in positive characteristic case because there is no notion of rational singularities, but there is notion of integrability, and we can just assume that we know that the form is integrable on each fiber. Whether it means that these values, these integrals, are locally bounded. So if you know how to solve it in positive characteristic, tell me, because it implies kind of 50 years old conjecture, which I don't discuss here, but we have some very specific map on which we know how to show that on each fiber the integral converge, and we don't know how to show that the integral converge to continuous function in positive characteristic. Okay, so some words about the proof. So the first step is to reduce to the case when dimension of y is 1. So of course you all know that if you have a function which is continuous along curves, it doesn't have to be continuous globally. But if this function is given by some reasonable formula, so somebody has to like work hard to construct a function which is like continuous in each curve and not globally continuous. And these functions, the density functions here, are given by, in a sense, reasonable formula. And for functions that are given by reasonable formula, if it is continuous along curves, then it is good. And now for one-dimensional case, it's not really hard. There is some work to do there, but basically we do resolution of singularities. But there you actually need to use characteristic 0 not only to construct the resolution of singularities and not only construct other resolution of singularities. You need some relations, some homological relations between top differential forms 5 minutes and other stuff. So yeah, you work with it and it works. But here we use some statements which are just wrong in positive characteristics. Okay, and so some general facts that are true for dominant maps or for, in fact, for generally smooth maps. So in fact, although we say that push forward is L1, but it has some better conditions. So it's basically the same line in the dictionary, but you can make it thicker. So if it's L1, you automatically know other stuff. So one thing that you know that the density functions, if it's okay, this is only characteristic 0, so locally dominant meaning generally smooth. So the density function is what's called constructible functions. So I will not give you the complete definition. Okay, it should be published here. So the definition of constructible function. So the ring of constructible functions is the ring of functions generated by absolute value of some nice function f and the length, the absolute value of such function. When f is in value in the local field, and I want to think about it as if it was a rational function, but in fact it is not a rational function, it's findable. It's not very far from being rational. Yeah, so this it took time until it had this formulation, so there are many people here, but it's not one joint work, it's several work. It gives you this result. And here also the same, but now here the result is that so we said that the function is L1, but in fact, if it's L1, then it's automatically slightly better than L1 plus epsilon. And what is epsilon? So there is a general proof that there exists such epsilon that based on this result, but it works only in characteristic 0. And then there is another result by Itai Glaser, Yotam Handel, and Sasha Sodin, when they prove that this epsilon have a very explicit bound in terms of, say, the complexity of phi, so how much data you need to define phi, say the degrees of all the polynomials involved. And then Itai and Yotam you use this result, so they kind of rewrite it in positive characteristic, and so this gives you this theorem in positive characteristic. This is kind of new, although this theorem is not true in positive characteristic, or not known and not understandable. So it seems that I ran out of time, so I'll just say what is the next topic. I will not formulate the result, but the next question was the other aspect, whether when are the dimension of this space of measure is finite, so how much different space of measure. So of course the space of measure is infinite dimensional because even smooth measures are infinite dimensional. So one thing you can do is take stocks of measures at a point. So here is the definition of stock of measure at a point, but the idea is that you consider a measure up to an equivalence relation, that two measures are the same if they're the same in a small neighborhood of a point. And for smooth measures, this is finite dimensional space. This is one dimensional space. Those are all constant. Now we're talking only in the piano. And but for non-smooth measures, so if you take the space of measures obtained by push forward, it might be finite dimensional, might be not. And
so for over R, what is
over R, the stock is always infinite dimensional, even for smooth functions. So you need to define something different.
yeah, so
I don't know. And so this part of the stock is only over QP. And over QP, smooth functions are one dimensional. The stocks are one dimensional. And non-smooth, okay, so if you take all the measures that obtain as push forward, there might be infinite dimensional space, might be finite dimensionals. There are examples like this, like that. And we didn't find the complete answer to this question, but one direction a sufficient criterion for this to be finite dimensional. And I probably will not tell you about it. But if you want to ask me afterwards, I can tell you. That is it. Thank you very much.
Decided on last 2 pages.
So this is example when it's happened, or maybe this example is a very interesting example. You start with a matrix and map it to characteristic polynomial. This is exactly the example I was talking about before, that it's not, that I don't know to prove that the push forward have continuous or even bounded density. I know how to do it for characteristic 0, it's very classical, but for positive characteristic, I don't know, and I really want to, like this will solve 50 years old problem. Yeah, and then there is this criterion which looks horrible, but it's completely algebraic, and it's not necessarily sufficient, but it is sufficient, and criterion for this fine dimension.
What question?
Can you say anything profound for my beloved case?
What is your case?
Was on one dimension the same fiber is discrete.
Then everything is smooth.
Well,
So
that's about it.
Yeah, but you like this case globally, locally it's not interesting. Yeah, and this talk what about local properties? So I can't.
So it's a local case. It's a local Jacobian.
Local in analytic topology, and then
You have local and
yeah, this is very important conjecture. It was proven very important question.
Story part, general interest. Okay, so Randy, thank you very much. Well, this morning session is adjourned, and so the next time we will meet for 2:30, the same place.
After a brief lunch, right?
After a brief lunch